Uh, Whenever a solution takes place, there are three types of interactions of work. Initial interaction is that intermolecular forces between solute and solute, and intermolecular forces between solvent and solvent. That we call it solute-solute interactions and solvent-solvent interactions. So when you add the solute into solution or into solvent, then the solute molecules comes out of their crystal lattice and try to mix with the solvent molecules. And the solute molecules make some space within the solvent molecules by displacement method. And by that way, they develop interactions called solute-solvent. So if the solute-solute, there is new interaction, solute-solvent interactions is found to be stronger than previous solute-solute and solvent-solvent interactions, then the dissolution process is fast. And if the new interactions are weaker than the previous interactions, then the dissolution process is slow. Okay. Now we find if the dissolution process is highly spontaneous, means if the substance is highly soluble in water, in that case means the new interactions or liking for each other is better. So in that case, you'll find they try to liberate heat. And if it is weaker, then in that case, moment you add the substance in the solvent, in that case, you'll find that the temperature of the solution will decrease. So we have exothermic solutions and endothermic solutions. Now we try to apply our literally principle. In a exothermic solution, if you heat, then the solubility decreases. And if the endothermic solutions, if you heat, then the solubility increases. Now, if this is endothermic, but if it is non-spontaneous, then why this type of solute goes into solution? It is simple. We can explain it on the basis of entropy. Because in solid substances, molecule cannot move. Moment you put it in water, they have a wider area for movement, and they gradually come out, and they start moving because it is a homogeneous solution mixture. So it starts moving in all directions by which its entropy greatly increases. Okay. So as the entropy increases, the non-spontaneous process becomes spontaneous and the substance goes into solution. So this is the theory of solution. Okay. Now we are going to explain some typical solutions. Okay. The first one which I am going to explain, it is not in your syllabus. This is for solid say this is the solid solvent. These are the one. Okay. All right. And these are the solute. Very small. Okay. If they are very small, in this case, they will not displace anyone. They will go and enter in the space. Just like that. So you go to nursery school, you find moment the school is over, immediately the small child will come and the parents will going to put them in their lap. Or if they go travel by the taxi, you'll find suppose three parents are sitting behind, three babies are sitting on their lap. So no extra space is required. So same thing happens. If the solute molecules or this is also solid, this is also. Okay. So this type of solution that you get, okay, is a solid solution. Oh, I not got it. I'll draw it separate. Okay. So you mix it. It's a solid solvent and solid solute. Okay. So it is going to form what? So you'll find here. These spaces are called interstitial spaces. So this stable solution is known as interstitial solid solid. Okay, interstitial solid solid solution. Now, example. Let me give an example. Say it is iron, and this is what? Carbon. So when you mix carbon with the iron, what do you get? You know, you get steel. So steel is a solid solid solution. Draw. This is not your given in your book, but you should know.
Done, sir.
Okay. So this is one. Write this one on the top. Right. Interstitial solid solid. Okay. Second one. I'll write the name later. Okay. See here. This is the solid. This is the solid. Solid. Look, their sizes, they're almost same. Now they cannot go in between. What will do? If you mix it, you'll find that the sizes are same. They will come and displace some of them. Okay. So what will get now? Okay, I got just identified. All right. Ink finished. Okay. Now see, it will be like this. They will displace. It may be like this. Okay. Because the sizes are same. So this one will fit in the size of the other. So whenever they displace anything in chemistry, what we say? We call it substitution. So this is an example of substitutional solid, solid. Now if I write the example, this is zinc, this is copper. So if we mix copper and zinc together, what do you get? Any idea? Don't sleep whenever I ask you a question. What do you get when you mix copper with zinc? No idea. Hmm? You get that? Brass. So it is a, what do you call this one? We call alloy. This one we don't call alloy. We call it this one alloy. So alloy is a substitutional solid solution. Draw.
That's all.
Okay. Okay, now see here. Now we'll go for B. Gas in liquid that solution to you all of you have seen gas in liquid solution. Huh? How many of you did not see? Just tell me. Gas in liquid. Hello. Whenever I ask you anything, do you hear me? Hello? Do you hear me?
Sir.
Yes,
Yes, sir.
sir.
Then why you do not say, either you say yes or you say no? Why do you keep quiet? Huh? Is it conservation of energy or what? So have you seen gas in liquid solution?
Sir,
Yes.
oxygen is in water.
Oxygen is present
Liquid
in
in
water.
water.
Perfectly all right. I agree. But do you visualize the gas there? Do you see gas molecule? Oxygen molecule you see in water? Hmm?
No, sir.
Hello.
No, sir.
No.
Huh? Acha. Then Miss Pal, Gitanjali Pal,
Yes, sir.
any of these so-called cold drink that you say, these are actually called, a chemist tells it carbonated water. Moment you open the bottle, do you not find the bubbles are just coming up from there? Hmm? Okay. So these are the example of gaseous liquid. All right. So we find how this how the gas is being dissolved in water. Gas is being dissolved in water by forcing carbon dioxide into water. So what you find that the more pressure you apply, more will be the amount of the gas dissolved in water. So we find that the amount of gas dissolved in liquid solvent is directly proportional to the pressure of the gas above the surface of liquid. The amount of gas dissolved, I will not write the amount. All right. The mass of gas dissolved in liquid solvent is directly proportional to the pressure of the gas above the surface of the liquid. Okay? And this rule is very, very important for you. It's called Henry's law. So what do you find here? If m is the mass of the gas, it is directly proportional to P. Or m is equal to Kp. So where m is equal to mass of the gas, P pressure of the gas above the solvent, then A is called proportionality constant.
Done, sir.
Okay. Now, as I told you, the concentration of any solute can be expressed in two ways. Either we can express by mass of the solute, or we can express in the term of mole fraction. Okay. So the Henry's law is being modified by John Dalton. Okay. Dalton had modified the Henry's law by incorporating mole fraction. Okay. Now what is this? What does it say? The mole fraction of the gaseous solute present in the solution is directly proportional to the partial pressure of the gas. Okay. Now, why does he say partial pressure? So let me show you. Don't laugh at my drawing, huh? Is there any bottle like this? For any carbonated drink? You have tasted all types of carbonated drink. Any bottle like this? Huh? This is the only bottle which I can draw. So this is the, yeah, up to this much is the liquid. See now. Gas is also there and the liquid is also there. So some amount of gas escapes and it is here. Here the gas. Okay. And some amount of the liquid also is evaporated. So these are these L. So the total pressure is the sum of the pressure of the gas as well as for the liquid. So because of that, we say partial pressure. All right. Okay. So if I say let X be, in your book they have given only X. Okay, let me write it. So it is not X, it is chi. Be the mole fraction of the gas, and P is its partial pressure. Then what I can write? Then chi is proportional to partial pressure P. Or I can write chi is equal to K prime I have to use K prime because I have already used K there because of that. So what is this? Where K prime is proportionality constant, or I can write P is equal to 1 upon K prime chi. See, K is a constant. Inverse of constant is also a constant. If 2 is a constant, half is also a constant. Okay, so therefore I can write P is equal to K H. There is not a multiple, it's a symbol. Okay, where KH is called Henry's constant. Example.
Done, sir.
Done, sir.
See here, very interesting. This is the solubility of the solute gas molecules. If see, if this value is high, then this will be low. And if this value is high, then this is low. Please remember. So we can determine the solubility of a gas from the value of the proportionality constant. The the degree of solubility of a gas in a specific solvent is known from the value of H. Okay, so if KH is large, then chi is less. You can say why? See, the product of both of them is equal to P. Pressure you made constant. Suppose you are dissolving a gas with 300 atmospheric pressure. So 300 is constant because they are applying through a machine. You can see in the pressure gauge. So if it is constant, if this value is high, this should be low. And if this value is low, then this should be high. If KH is large, then chi is less. Or vice versa. Given, they will give you some value and ask you to arrange them in order of solubility. So please remember, if the KH is large, solubility is minimum. And if the KH is less, then solubility is more. And if the KH is least, solubility is highest.
Done, sir.
Okay. Now we see limitations of Henry's law. Henry's law cannot be applied for all cases. Henry's law is not applicable to at low temperature and high pressure. Why at low temperature is not applicable? In low temperature, the solvent molecules will come so close to each other. In that case, they will not allow this gas molecule to come in between them. And if you use high pressure, so much of gas that you are going to force inside, okay, forcefully you are dissolving it. So in that case, this is also not applicable. Second, it is also not applicable to those gases which react with solvent molecules. That is, when either they undergo association or association in solvents. Write down, I'll explain. Not applicable when you dissolve ammonia in water. Okay. Henry's law is not applicable to NHC. I'll write one example and show you. So I have this sentence is not complete. See here. In NH3, moment you put this, you will find it will form ammonium hydroxide. That is it, associate. It is combined. And after some time, what will happen? Ammonium and this. So it dissociate. You cannot imagine there. More than 600 volume of ammonia is soluble in 1 volume of water. Just imagine, the solubility is so high. 7. Sulfur dioxide, H2O. H2SO3. SO3. Okay. Then it dissociates to give you 2H plus SO3 minus. Low. SO3, H2O, H2SO4, associate. It associates to give you 2H plus and SO4 2 minus. Then this is your famous cold drink. See, it gives you H2CO3. It gives you 2H plus and CO3 2 minus. Because of that, you should not take extra too much amount of the cold drink. It increases the acidity in your body intestine. So these are not applicable for them. Okay. Now I don't know who told me that oxygen. Huh? Oxygen is dissolved in water. So what type of gases are there where you'll find that it will follow Henry's law? So Henry's law is followed by the gases like hydrogen, oxygen, nitrogen, huh? Okay, etc. But again, for your example, the solubility of oxygen in blood does not follow and this. But you will tell, sir, blood also contains water. Then why you should not follow? See there. When you inhale oxygen, when you inhale air, oxygen is being absorbed in the blood, but not the carbon dioxide. Why you know? Because oxygen associated with the blood. What do you get now? O2. No, I don't write. So this what? So please for your entrance exam. Henry's law is not applicable if you dissolve gas at low temperature, dissolve gas under high pressure, and if it undergoes association and dissociation. Okay. Now one more example I did not write. All these association and dissociation. Another example, please, like HCl. More than 700 volume of HCl is soluble in 1 volume of water. Why? Because see what happens now. What it undergoes? Undergoes dissociation. So this is This is also carbonated or aerated drinks. From there we could understand, then we can dissolve more and more amount of the gases in water by applying more pressure. After that, this business of carbonated water has started. Okay. Now, second is in deep sea dive or scuba dive. Okay. You have seen so many movies also, you have seen National Geographic, Discovery, in all these places. And there, suppose this is the sea, and this is the person. Okay. Like this, now. Then he carries a cylinder on the back. Okay. This is the one. So what does he carry in the cylinder? A cooking gas or what? Hmm? When the divers dive into the sea by putting a cylinder on his back, what does he carry? Does he carry
Oxygen.
oxygen? Okay. Suppose if he carries oxygen, if it is 100% oxygen, now you find that everywhere we are talking about the oxygen. Okay. If he carries 100% oxygen, if he inhales, this fellow will die. You know why? Our atmosphere is a boon for us. In atmosphere, we have only 20 to 22% of oxygen. If you inhale pure oxygen, in that case, your metabolism process will be so fast and so much of heat will be generated, you will feel sick. So he carries compressed air. Compressed air contains what? Compressed air contains the same composition, 76% nitrogen, 22% of oxygen, some amount of carbon dioxide and other gases. See, when it goes down, this is being filled up in what? When he is there, when this fellow is here, okay, he is under 1 atmosphere. So when he inhales the air, oxygen is being absorbed by the hemoglobin. The rest of the air are not needed. It goes out. Nitrogen goes out, metabolism process, carbon dioxide goes out. Okay, so only oxygen get dissolved in the blood. Okay, so O2 plus Hb goes into Hg. The rest of the gas goes. When he goes down, say this is the height. What is the pressure now? He feels the pressure of pressure is equal to Huh? So suppose I write here atmospheric pressure plus an extra pressure of H rho G. H is the height of the water column above it. Rho is the density of water. Density of sea water is much, much higher than the normal water what we drink because it contains huge amount of mineral. And this is the gravitational. So under this force, because pressure is very high, nitrogen gas get dissolved in blood. Nitrogen is not absorbed, is being dissolved because blood fluid contains what? Water. All right. So now he starts coming. Now he is going. Okay. So he is coming up. We find this. Now, if this is the vein, see, nitrogen was dissolved in the gas. Like when when you don't open the bottle of carbon dioxide, you find carbon dioxide is there, but you can't see them. When you open it, you find the bubbles are started coming out from the water. All right. So when it starts coming up, then the pressure decreases. Then the nitrogen, which is dissolved in the water, this comes out in the form of bubble. See, these are the nitrogen bubble comes out. It comes out from the blood. See what will happen? Through vein, blood is supposed to move. Now the nitrogen bubble has come up and it blocks the passage of blood. Okay. Huh? So when the divers start coming up, pressure decreases and nitrogen gas in the form of bubble starts in the form of bubble comes out and block the way. Okay. See, this is extremely painful. And if it blocks the cerebral vein, the vein which is there in your brain, it's extremely painful. and sometimes leads to the death of diver. That's Majin. Many people earlier used to die because nobody knew why they are dying like that. So those days people knowledge is less. People will say ghost is there. All right. But now we find the disease is this one. Okay. This is called, the disease is called band. The disease is called band. So now we do not want that diver should die. So what to do? We have to somehow stop the solubility of nitrogen in blood fluid. Okay. So in this case, what is being done? Hence, to stop the solubility of nitrogen in blood, air is diluted with helium. When you mix helium, in that case, the solubility nitrogen does not get dissolved in blood. Okay, let me see the composition. In helium is 11%. Eleven 11.7% nitrogen, 56.2%, and oxygen 2.1%. So this cylinder now contains this. Please remember, it's a very serious thing. So do not have a feeling that these cylinders contain only oxygen. Even if you are in cold water also, 100% oxygen means yeah, finish. You'll die. The presence of helium lowers the solubility of nitrogen in blood. Third, high altitude see as the divers goes down in water by taking air tank. Same thing happens when people goes for climbing high mountains. They also wear the same thing. But in that case, the air is there. Why they should take? Please remember, at the upper atmosphere, the concentration of oxygen is very less. When the concentration of oxygen is less, in that case, you develop a breathlessness, as if that someone is strangulating you. And when the amount of oxygen in your brain is less, in that case, you will find you will not be able to think properly. All right. Huh? So, what do you say here? In case of higher altitude, the air is thinner and contains less amount of oxygen. Okay. Presence of less oxygen develop breathlessness or and people suffer from anoxia. That is weakness and inability to think properly. Such thing can be avoided can be avoided by carrying air tank rich with oxygen.